I want to teach you one more algorithm. Now, here is the intuition of the other algorithm that I want to teach. So, that the algorithm that I taught you is called the value iteration algorithm. That algorithm that I want to teach you is called the policy iteration algorithm. These are brothers and sisters, right? They are very close to each other. The main point is that in value iteration, we want to come to this convergence of V star function, and we are constantly moving in the value space, and we can always compute the greedy policy, but we are never insisting that the greedy policy ever changes in any iteration. It is possible that I make many value changes and then my greedy policy finally changes. See, value function space is it's uncountably infinite space, but how many policies do we have in our domain? We have a finite number of policies. So, what is happening is that we are trying to get to a policy which is a finite, one of the many finite policies, but we are moving in the uncountably infinite space. So, why do not we flip it around? Instead of moving in the value space, let us move in the policy space. Then we may have to move smaller number of times hopefully, and we will be able to get to our optimal policy sooner. That is the hope. So, instead of searching in the value space, let us search in the policy space. Instead of computing the resulting policy from a given value function, let us compute the resulting value from the given policy. This algorithm is due to Howard, from again going back to the 60s, and is called the policy iteration algorithm. Now, the idea is very simple. As we initialize the value function as V0, we will initialize a policy as pi 0 arbitrarily. Assign any action to any state, does not matter. Then you repeat two steps. You first figure out how good this policy is, and then you make a move in the policy space so that you are better than the previous policy. So, in other words, how do you compute how good this policy is? You compute Vn plus 1, which is the evaluation of the pi n policy, and then you compute a new policy as one step look ahead of the Vn plus 1 function. One step look ahead, greedy policy. And your convergence condition is no longer that your Vn and Vn plus 1 are very close to each other, it is that your pi n plus 1 and pi n is exactly equal. Because if you took one step greedy policy and you did not change your policy, that means you have converged, you can stop here. So, termination condition is much better defined, you do not have to put in an epsilon here. The advantages are that first of all, I will be searching in a finite space as opposed to searching in an uncountably infinite space. Therefore, I can hope that my convergence will be in fewer number of iterations, and believe it or not, all my properties will follow. In fact, I can prove that pi n plus 1 will always be better than pi n or equal when I converge. So, I am always making progress. Think of it as local search in the policy space, but in this very specific case where when I move up I will always be improving, and when I stop I have found the optimum. There are no local optima. Now, how do I do this policy evaluation? I do policy evaluation using the methods that we just discussed earlier, where I am given a policy, I want to evaluate it. This policy evaluation unfortunately takes order n cube time and therefore is considered costly. Oh, iterative policy, you can solve a system of linear equations. You will have values for each and every node in the graph, yes. How do we define the evaluation of the policy? Well, this is what we did last class. So, let me remind you. See, we first started by the brute force algorithm, and the goal was evaluating each policy. So, how did we evaluate a policy? We said what is the expected cost of reaching the goal starting in that state and following that policy. And we have developed two algorithms to achieve this. One is solving the system of linear equations, right, which can be done in order s cube time, and the other is the iterative policy evaluation. So, we will do exactly that, right. So, the goal there was, given a policy, can I compute the value function, and that is exactly what I am going to use in the policy iteration algorithm. Because this is costly, I could also approximate it. Now, why is it costly? Because I have to solve the system of linear equations, that takes order s cube time, but I do not have to fully solve it and then change the policy. Well, I can approximately solve it and then change the policy, and then I can approximately solve it and then change the policy, and just approximate the policy evaluation step. And when I approximate it with approximate this, then this is called modified policy iteration. So, what is modified policy iteration? It says initialize the pi 0 arbitrarily, do policy evaluation, which is V n plus 1 be the approximate evaluation of pi n, and then do policy improvement, as pi n plus 1 is argmax, exactly what we used to do. The advantage is that it is in practice a faster algorithm. It is probably the most competitive synchronous dynamic programming algorithm. So, synchronous. So, let us understand the word synchronous. The word synchronous means that in one iteration I go over all states synchronously, one after the other. That is called the synchronous dynamic programming algorithm. So, typically value iteration takes many more iterations to converge, policy iterations takes very few. In fact, policy iteration is somewhat of a theoretical curiosity for some of the researchers. So, there is a research by the researcher by the name of Shivaram Kalyan Krishnan in IIT Bombay, and he has been thinking about policy iteration, and what he has found is that the bounds for the number of iterations in policy iteration are too weak, and in practice policy iteration gets done in like 10, 20, 30, 40 iterations, very few iterations. It is very surprising. He has not been able to reconcile the bounds, theoretical bounds, and the empirical analysis. It is possible that there are better bounds that are lurking behind policy iteration and number of iterations behind policy iteration, but he has not been able to solve it, right. So, think about 1960s algorithm. We still do not understand some things about it theoretically, or we do not have tight enough bounds. So, at least experiments show that it converges much faster, at least in the number of iterations. Unfortunately, each iteration becomes more expensive because you have to do this policy evaluation. But if you implement this right, then this becomes probably faster than value iteration. Okay? Yes, question.
When you are doing approximate evaluation, then you might the fixed point that you are taking that might not be optimal.
Very good. So, Vishwajit makes an important point. He says, if I am doing approximate evaluation and if my termination condition is pi n plus 1 is equal to pi n, then am I guaranteed to hit the optimal? No, because I have only done approximate evaluation. It is possible that I did not evaluate it right, and therefore, the greedy with respect to the approximate evaluation convergence is not enough for guaranteeing optimality. So, what can I do?
I think in that case you can calculate whenever you get pi n plus equal to pi n, then calculate true value.
Correct, very good. So, see, this is exactly how you do algorithm design. So, whenever you get pi n plus 1 equal to pi n, you realize, oh, it could be because I have converged, or it could be because my evaluation of the policy was approximate. So, what do? You evaluate the policy exactly, then recheck if pi n plus 1 is equal to pi n. If it is, you are done. If it is not, you keep going. Very good. That is exactly what people do in modified policy iteration. Any other questions? There are a lot of applications to Markov decision processes. any kind of game in which there is a probability. Have you played the 2048 game? There was a time 3-4 years ago where even my students in the class were constantly playing 2048. Is it a Markov decision process? At every point I have a state, and in the next I can make one of the 4 moves, and in the next something deterministic happens, and then one of the 1 or 2 randomly appear in one of the open places. You can model it in the probabilistic transition. That is a Markov decision process. A lot of your cell phone games where you are given some actions and something randomly happens, those are the Markov decision process. In robotics, just navigation, because you have to constantly deal with uncertainty, is a Markov decision process or its extension. Okay. In finance, when I have to figure out whether to invest money, whether to buy shares, sell shares, or not do anything, it's a long term problem because the value may change, go up, go down, that is a probabilistic transition, and I want to do an action that maximizes my long term money. That is also a Markov decision process. Now, there can be some problems. For example, I do not know whether exactly the probability with which share is going to go up or going to go down. So, I may have to learn these probabilities, I may have to add some insight into how to define the Markov decision process. That is a different story, but the fundamental formalism would be a Markov decision process. A colleague of mine at University of Washington was working on radiation planning for cancer. So, he said that I have to give radiation, there is a cancerous tissue that I need to kill, there is good tissue around it that I need to save, and I want to maximize the cancerous tissue and minimize the other tissue that I hurt, and then I can send radiation at different angles with different intensities, and I have some probability function of how it kills various tissues. Now, I have to do long term radiation planning. It is a Markov decision process. He modeled it as a Markov decision process. There are many such scenarios where the future is uncertain. Like for example, do I give more chicken or do I give more vegetarian food in Air India? I have so many seats, I have so many meals that I can provision, what is my balance? Some people have booked special meals, but what about others? I do not want to be in a place where lots of chickens have gone away and more people want it and it is not enough, and vice versa. Again, you do not know what people are going to ask, you only have a probability distribution, right? And this goes on and on and on. Right? I recently found some forest firefighting problem modeled as a Markov decision process where they have to figure out how much water to pour at which part of the forest. Now, Markov decision processes lead to more interesting problems, and if we have time we will study partially observable Markov decision process where not only are my actions stochastic, but my world is not fully observable, and moreover sensors can be noisy. Now, this is the most general version of the problem, or one of the most general versions of the problem, because real physical robotics requires the world to be partially observable and the sensors to be noisy. Now, what happens is that I do not know the state, and if I do not know the state, then what do I know? I know some probability distribution over states. I do not know exactly where I am, but I have some distribution of where I may be. For example, suddenly my robot wakes up and it says that it is at the green dot and it needs to go to the red dot, but it does not know whether it is looking up or it is looking down, and it can't figure it out. So, what does it do? It goes straight and takes a right turn. So, either it goes to this point or it goes to this point. Here it sees whether it is a longer corridor or a smaller corridor. As soon as he sees it, it knows that it is either now here or here. Based on that, depending upon where it is able to come back to the red dot. Whereas, if it did not know and if it started going left, it may have been going like this, but it may also have been going like this, it would not have been able to figure out where it is. So, here it has a belief, the belief is either it is facing up with probability half or it is facing down with probability half. And this kind of problem is modeled as a partially observable Markov decision process. There what happens is that you do not maintain the state, you maintain a belief over the state space and you make an action based on the full belief. Okay. So, I want to stop, we will see if we have time to study MDPs, but I want to stop with this slide. I want to say that we have just basically introduced Markov decision processes. We have only talked about, like we have shortest path, Bellman-Ford and Dijkstra's, we have only done that. We have not even done a depth first search, breadth first search or an A star. So, in the world of Markov decision process, an A star algorithm becomes what is called the LAO star algorithm. So, it does both heuristic search as well as dynamic programming together. Okay. Then in practice, people also study hierarchy of MDPs. For example, if I have to figure out how to get to Montreal, then I would not start planning that I will go forward, then go forward and then slowly get to the car and then open the car. I will not create that. I will divide it into sub goals. So, I will say first I will get outside this building, then I will get to the car, then I will get to the airport, I will park the etc., etc. And then I will further subdivide the problem and then further subdivide it into specific actions. So, Markov decision processes, you do not solve the full blown Markov decision process, you first decompose the problem in practice and then you start solving each MDP separately. We already talked about MDPs. The next thing we are going to study is probably the most important thing. Some people say that AI is reinforcement learning. Like we have had ideas that AI is search, AI is knowledge representation, we will also do AI is RL view. And so, what we are going to study next is what is reinforcement learning and what are the algorithms for reinforcement learning. In terms of our view, what is RL? RL is an MDP where the rewards and transitions are not known. So, you have to learn, you have to do machine learning, you have to learn rewards and transitions and then you have to figure out which action do you execute. That is what we are going to study starting next week. We will stop